Welcome to this explainer. I want you to think of today's session as an executive boardroom pitch masterclass, but for your Cambridge Mathematics AS and A-level exams. From rendering complex 3D video game graphics to calculating precise global flight paths, vectors are quite literally the mathematical DNA of our physical world. Today, we're taking on one of the most high-stakes client briefs of the entire syllabus, Topic 3.7, Vectors. Look, if you're aiming for top marks, understanding the underlying mechanics of vectors isn't just an option, it is an absolute necessity. You need to structure your exam responses with the clarity and authority of an executive consultant. So we're going to look closely at what the syllabus actually demands, and more importantly, what the examiners, your most demanding clients, are really looking for when they audit your papers. Okay, let's dive into this. Our agenda today is broken down into 5 parts. 1. The vector challenge. 2. Core theoretical principles. 3. The procedural framework. 4. Top 3 examiner warnings. And 5. Evaluative exam strategy.
Section 1. The vector challenge. Why topic 3.7 matters. So why do students find interpreting complex 3D spatial scenarios so incredibly hard? Well, to answer that, just look at this direct quote from a senior examiner. They state, mastering 3.7 vectors is essential for Cambridge Mathematics success. This topic appears in every examination series. I really want to emphasize that word, every. You literally cannot hide from vectors. There is absolutely no combination of exam papers where you can dodge this. If you're sitting for the 9709 exams, you will face this topic. Understanding that it's unavoidable is the very first step to mastering it.
To make sure we're all completely on the same page, let's explicitly define our core deliverables for Topic 327. In this specific Cambridge context, we're looking at a conceptual framework anchored by 3 main pillars: the scalar product, calculating the angle between lines, and determining the foot of a perpendicular. Now, why do these matter so much? Well, the scalar product is essentially your ultimate tool for proving perpendicularity, right? And that unlocks the rest of the geometric puzzle. You need to be ready to execute all 3 of these flawlessly.
Section 2. Core theoretical principles beyond memorization.
Look, there is a massive difference between the rote memorization of vector formulas and building a connected conceptual understanding. Think of memorization as showing up to a pitch with just a generic template. The syllabus heavily favors candidates who exhibit real strategic understanding. Memorizing the dot product formula is easy, sure, but building a conceptual framework based on established geometric principles, that's what allows you to handle those nasty, unfamiliar contexts. When you open an exam paper and see some bizarre 3D shape or a spatial scenario you've never encountered before, that deep conceptual anchoring is exactly what saves you from panicking.
The theoretical architecture of Topic 3.7 rests on 3 things: precise definitions, causal relationships, and cross-topic connections. Now, what do we mean by causal relationships in a math context? It means understanding why an equation actually works. For instance, realizing that setting a scalar product to 0 is the algebraic cause that guarantees the geometric effect of a 90-degree angle between 2 lines. Furthermore, cross-topic connections are vital. Examiners love candidates who can link vector algebra back to core trigonometry or basic geometry. It shows mastery over the entire mathematical universe, not just one isolated little bubble. Before we go any further, I need to raise a massive red flag straight from the principal examiner reports. Consider this a critical risk assessment. Always define your terms before using them in extended responses. For example, examiners constantly see students confusing a position vector, which is a specific fixed point of space, with a direction vector, which is simply a line of travel. If you start calculating without explicitly defining which one you're using, the examiner cannot follow your logic, and they absolutely will not give you the marks. By the way, to ensure your academic portfolio remains highly competitive, subscribe to our channel at Ace the Exams and enable notifications for our weekly consulting insights. We drop these masterclasses all the time.
Section 3. The procedural framework, the method mark strategy. Let's see how this builds. Think of this sequence as your ultimate safety net, your standard operating procedure. Systematic processing within vector problems follows a very standardized sequence. Step 1, identify the given information. Step 2, apply the relevant geometric principles. Step 3, execute your analysis with completely clear algebraic working. Step 4, verify your results. And step 5, present it in the appropriate format. Even if you punch the wrong final number into your calculator under extreme exam pressure, showing this exact deconstruct, solve, evaluate sequence guarantees you capture those highly valuable method marks. And speaking of that final step, the examiners have very strict executive conventions for how mathematical information should be displayed. In A-level maths, this means clearly distinguishing scalars from vectors. Are you using column vectors? Are you using the correct I, J, K notation? Clear working and annotations are totally non-negotiable. If your notation is messy, your logic becomes impossible to audit, and the examiner is definitely not going to hunt for your correct answer in a sea of scribbles.
Section 4. Top 3 examiner warnings. What not to do. Let's look at the biggest pitfalls straight from the grading floor. Warning number 1. Examiners report that students consistently confuse cause and effect within vector problems. In vectors, getting this backward usually means a candidate assumed lines were perpendicular to find an unknown constant, rather than properly proving they were perpendicular in the first place. You must know exactly what is a given fact in the brief and what actually needs to be proven. Don't put the cart before the horse.
The second major pitfall is completely forgetting to check the final format. There is literally nothing more tragic for an examiner than seeing a flawless, beautifully executed page of complex scalar product calculations end in 0 marks just because the candidate couldn't be bothered to write the final coordinate properly or left a vector in the wrong format. Please do not let your hard mathematical heavy lifting go to waste over basic presentation errors.
And the final warning, providing generic answers. Your mathematical response has to be tailored to the specific geometric scenario presented. A generic formula dump for finding an angle just won't work if you haven't actually identified the correct direction vectors for that specific 3D shape. Always ground your math in the specific context of the question.
Section 5. Evaluative exam strategy. Thinking like a top scorer. Now, what's really interesting about this slide is how we bring it all together. While vectors might not immediately seem comparative, high-level multi-part questions often require evaluating different mathematical methods. Look at this breakdown. Can you identify the similarities between solving a problem with a pure geometric approach versus a strict algebraic one? For evidence, you need to extract the concrete data, like the specific coordinates or direction vectors, to prove which method is more efficient. And finally, you draw a conclusion to execute the absolute best strategy. This structured analytical thinking captures every available mark.
Top-scoring candidates constantly evaluate their work, just like a top-tier consultant reviewing a proposal. Evaluating evidence in math means rigorously checking your assumptions. Did you blindly assume 2 lines intersect when they might actually be skew lines just flying past each other in 3D space? Does your final calculated perpendicular distance logically fit within the bounds of the shape given? Identifying limitations and justifying your decisions with hard, undeniable mathematical proof is what separates an average student from a truly exceptional one.
So, as we wrap up this boardroom pitch on vector mechanics, I want to leave you with this final critical thought. Are your geometric assumptions completely justified by the math? The next time you tackle a vector problem, don't just mechanically calculate, evaluate. Verify your frameworks, check your definitions, and make sure your working is crystal clear. Apply this exact executive standard to your next past paper, and you will see the difference. To ensure you keep mastering these concepts, you need to subscribe to AC Exams right now, hit that notification bell, and leave a comment below with your current level and target subject. Thanks for joining me on this explainer, and keep practicing.